Hi, this is Lab 2, Motion of Falling Object. I recorded a video of a falling object, analyzed it using Tracken, and made models using VIDAR. So for the object to be, so if the object was falling, that means that it has a non-zero net force acting on it. And the change in velocity does not equal zero, so the object is accelerating. I set the calibration stick as the height of the cup, which is 12 centimeters, and the coordinate system at the center of the cup, with the positive y-axis pointing up. Here's the video. And here's some of the object's properties. The mass is 15 grams, the height is 12 centimeters, and the initial position and the initial velocity are both 0. So, in the first model, I assumed that the only force acting on the object is the weight force. And the weight force is equal to minus g times mass times j hat. And g is the acceleration due to gravity, and j hat is the positive y-axis. So the minus here indicates that it's moving in the negative y-axis. Let's see it in. Okay. Here's the mass and the initial conditions. As you see here, the only force acting on it is the weight force. It's on it. Okay. In the second model, I assumed that the weight force and the drag force are the only forces affecting the object. I can represent the drag force with both of these equations. I just did this one, which is negative b times the magnitude of the velocity times the velocity, which is the velocity here is a vector, so it's a magnitude and a direction. And here's the p constant, which is 0.00333 kilograms per meters, or Newton in seconds squared per meter squared. I determined the p constant by guessing it into the final position matched the real observation in Tracker. And let's see it. As you see here, it's the same as before, but with the p constant and the drag force. Here's the magnitude, and here's the velocity vector. Let's run it. So for the air scale, I decided that the air's length is 2 meters long, so I divided 2 by the weight force, and I got 13.6 meters per Newton. And here's a graph with the experiment model with drag and model without the drag. The experiment and the model with drag are identical, but the model without the drag is a bit off, and that's because it's faster, because it has no air resistance or drag force. So what does it mean? Which models, if any, predict a terminal velocity? A terminal velocity is where the drag force and the weight force are equal, but in the opposite direction. So they would cancel each other out, and we'd have we'd have a zero net force, so a constant velocity. And as you see here, I did not have a constant velocity because the time interval was short and the height was not long enough. So what if the object was initially thrown downward but not dropped from the rest? Would the terminal velocity be the same? Of course not, because if the object was initially thrown down, then it would have an initial velocity. So here I changed it so it would print the final velocity, and here it dropped from rest because the initial velocity is 0. Let's see the final velocity. The final velocity is negative 4.2, but if we change the initial velocity as if it was thrown downward, here's what the initial velocity would be: negative 6.2. So yes, it would be different. That was lab 2. Thank you for watching.